Alrighty, we are going to go ahead and get started. Today we're going to be doing some diffusion model generative stuff. Specifically, we're going to be looking at DreamFusion. This is a variant of kind of the diffusion work, except it's really about 3D, right? So going from a text-based prompt to a 3D model. So this is just some examples here. Of course, these are kind of the cherry-picked paper examples, but we have this monkey, a chimpanzee dressed like Henry, the eighth King of England, and you can see how if you rotate, you have a actual 3D mesh in this. Pretty impressive stuff, and honestly, if 2D image generation was gonna be extremely disruptive to the art community, 3D generation is going to be absolutely insane, because video games, there's so many things where 3D modeling is very difficult, and there's a lot of people who make their living doing 3D modeling, and being able to create 3D models with just text is going to be absolutely insane. So this is still very early on. This is work out of Google Research coming from Ben Poole. There isn't a GitHub, but there is I did find a PyTorch implementation of this code, or of this paper. It's not quite the same. So, blah, 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 work in progress. So, yeah, they don't have the image gen model. The image gen is basically Google's version of the stable diffusion, right? What am I trying to do here? I'm just not on the right. There we go. Image gen. Right, so image gen is Google's version of the image creation. But that's not publicly available, so the guy who made this used stable diffusion, especially this implementation here, diffusers, Hugging Face implementation of it. Different from image gen, stable diffusion is a latent diffusion model which diffuses in a latent space instead of the original image space. Okay, so what does this mean? Maybe we can look and find a little picture here, and this will help us understand. So diffusion, you can think of it as basically adding noise and then removing that noise. That's what these models are basically based around. But it basically, as far what the user here is trying to say in this comment is that in image gen, you're diffusing directly in this image space, right? The image of this frog, that's where you're adding the noise and then diffusing it out. Versus in stable diffusion, you're not doing it directly in image space, you're doing it in this latent space. So you're doing it to a vector. I don't know, there's not really a good representation of what that vector looks like, but there's a vector that represents the image, obviously encoded with some neural net, and then they diffuse in that space. So blah, blah, blah. Therefore, we need to propagate back from the autoencoder. This is interesting because variational autoencoders encoder. Double use of the word encoder, which introduces extra time cost. 1,000 training steps take about 3 hours to train on a V100. What's a V100 here? V100. Let's hit back here. Shopping. Yeah, V100s. These are big boy graphics cards. These are $8,000 graphics cards. That's not what we have here. We have something much smaller. We have a 1080 on this computer. But no worries. I think we're just trying to kind of play around in this repo and see what happens. Okay, what other kind of noticeable differences here? We use the multi-resolution grid encoder to implement NERF backbone. Instant NGP, so this is kind of a NERF paper. This is the NV Labs, which is the NVIDIA research. Okay, this is a relatively active repo. You see here they're still making updates up until 2 days. Neural radiance field. Okay, different implementations of that. CUDA, NVIDIA GPU. Okay. Implementation from, okay, wait, so they're not actually using, they're using this implementation here of NERF rendering. PyTorch implementation of the sign distance function and the neural rendering function part, grid encoder, and the density grid ray sampler in instant. So different PyTorch implementations of NERF stuff. Okay. Much faster rendering. 800 by 800 is a pretty big image size, 10 frames per second. I wonder if that's also on their V100 though, which has a lot. How much memory? Memory of V100. 32 gigs of a V100. Oh no, okay, the standard size is 16, so maybe that's the one they're using, hopefully. To do, alleviate the multi-face Janus problem. So, Ben Poole is the original author here of the paper here, so this is probably the leading expert of 3D generation using diffusion models, and he talks about, so if we actually go to the gallery for this paper here, or for this code base here, he posts some models that he's generated using this, and there's a bunch of these that suffer from this issue where you have multiple faces. It's kind of like it's not consistent, right? It doesn't have a semantic understanding of like the head having 2 eyes and there being a back of the head and all of that. It's just kind of almost combining a bunch of 2D images into a 3D shape. And Ben Poole calls this the Janus problem. Janus being the Roman god of duality, I suppose, and him has 2 faces. Okay. View-dependent prompting helps, but it doesn't solve it in all cases, as seen with the dream diffusion model of the squirrel. So they still haven't implemented shading or view-dependent prompts. Maybe a few more hours. Those help a ton. Okay. So view-dependent prompts. What does he mean here? Okay, so guidance is not known. Training must provide a text prompt. Okay. So ref text is the actual prompt. And then directional text, guidance.get text embeddings of reference text. Okay, so there's an option here where you can provide different views of the text. Right here, you're just taking the original reference text and then basically expanding the prompt to also have something like the overhead view of that. And then that's what you're using for the guidance. You get the text embeddings of that and then feed it. Okay, this is just like one giant script. Dream Diffusion. Let's actually go ahead and download, try to get this working. So let's grab PyEnv. Let's go ahead and create a, let's call this DreamFusion. Okay, PyEnv activate DreamFusion. Okay, so now we're inside a Python virtual environment called DreamFusion, so it allows us to kind of install the right things and keep the dependencies separate on our computer. We're going to go ahead and clone this repository here. Bam. All right. cd dev. All right, I think we fucked up here. Let's move out rf stable diffusion. Let's go into our dev folder and then git clone it into that, and then cd into stable DreamFusion. All right, so we're now inside the folder. Let me make this a little bit bigger. I think that's a little too small for you guys. Maybe that's a little bit too big. Maybe like that is a happy medium. Okay. To download the stable diffusion model checkpoint, you should provide your access token. You can choose either of the following ways. Run Hugging Face CLI login and enter your token. Okay. Okay, so we don't have the Hugging Face CLI. Let's Hugging Face. You'd think they'd make this easy to find. Hugging Face, is there a community website? Hugging Face install CLI. Quick start. Pip install Hugging Face hub. We don't want the hub, we want the CLI. Okay, actually it seems like that's exactly what we want. All right, let's put that in there. Oh, notice to update, we've got an old version of pip. Let's update pip as well. All right, let's log into the CLI here. All right, we're going to move this away and we're going to get our token, just so you guys don't see it. Copy. I'm gonna put it in here. Invalid token. New token. Name. Trend 2. Copied. Hugging Face CLI login. Paste. Token has been saved. Okay. So we now have our Hugging Face token. Let's go ahead and pip install the requirements. Let's see what the actual requirements are. So we have Torch, PyTorch, Ninja, TriMesh, OpenCV. This is a huge dependency, right? Oh no, guys, that's my token. Hopefully you can't freeze the frame and watch that, but we'll see. Jesus Christ. OpenCV Python on PyPy. Latest version. Release history. 197 million downloads. That's popular. Okay. What else? We have Torch, NumPy, Pandas, TQDM, which is the little loading bar, SciPy, Hugging Face, Transformers, Diffusers, ImageIO, ImageIO FFmpeg, scikit-learn. Alright, cool. Let's go ahead and install these. Pip install -r requirements.txt. That's going to take a second. There's OpenCV. It's 69 or 60.9 megabytes. So quite the thick boy. Today I'm drinking some espresso. That's how real people drink coffee. Super dark. Grows hairs on your chest. Alright. Looks like it installed. All the requirements. No errors. Alright, let's go ahead and install nv-diffrast. So for exporting the textured mesh. nv-diffrast. Modular primitives for high performance differentiable rendering. This is again coming out of NV Labs, the NVIDIA research group. PyTorch TensorFlow library that provides high performance primitive operations for rasterization based differentiable rendering. Right, rasterization is just kind of going pixel by pixel down an image like this. And then differentiable rendering is the type of rendering that's used in NERF, right? Neural rendering functions. And because it's differentiable, you can basically do it with a neural network and propagate gradients, and that's why they use this form of differentiable rendering. Okay. This is seems like it's just one guy who keeps pushing code to this. Distinguished research scientist at NVIDIA, PhD. Let's follow this guy. Okay. Looks like it installed. Let's go ahead and also install the TCNN backbone. Okay, so TCNN backbone, what the hell is this? Let's see if we just search GitHub TinyCUDA. TinyCUDA NN. Small self-contained framework for training and querying neural networks. Fully fused networks versus TensorFlow. Okay, so this is basically a lightweight TensorFlow, right? PyTorch extension. Okay, so this basically seems like it's NVIDIA kind of creeping up the stack and eating TensorFlow and PyTorch's lunch. give that a star. We'll see where that ends up. I don't know if we need to necessarily use that backbone, the dash tcnn. Maybe let's just download it anyways. It might be more memory efficient, especially since we have a Tensor or an NVIDIA GPU. And then install clip guidance for the DreamFusion setting. I don't know what DreamFusion is, but error fielding. Okay, this error originates from a sub process with pip. Error legacy install failure. The detected CUDA version mismatches the version that was used to compile PyTorch. Please make sure to use the same CUDA versions. Okay, I think this is similar to the error we had on one of our previous videos where basically we need to get a newer version. Let's history grep pip. Yeah, we ended up installing a newer version of PyTorch. Let's go ahead and do that here as well. So this is going to be a PyTorch that works with 11.6 CUDA, which is the one that we have on this computer. Okay, and then also install clip. Put that in there. This actually installed Torch Vision. So pip freeze. We have so many things here. We have Torch Vision, Torch, the entire ROS RQT. Seems heavy. I wonder where that got installed. And then also TensorFlow. Damn, that's a lot. Okay. Build extension. By default, we use load to build the extension at runtime. We also provide setup.py to build each extension. Install all extension modules. Scripts install. Pip install ..ray marching, Shen encoder, frequency encoder, and grid encoder. Why don't we open up VS Code on this. Okay, and we can just look at this itself. So pip install ray marching. What is ray marching here? Wow, that is... What the fuck is that? Oh shit, and they're monkey patching it too. This is some very gross looking Python. Okay. CUDA, the installation here. I wonder if we actually need this. This is a lot of custom stuff here. So this is basically an implementation of the ray marching algorithm. Ray marching, let's go back to our Chrome here. Ray marching is okay. Interesting technique can be used to generate fully procedural from a shader. This is the type of rendering that they use for nerfs. Is this a GLTF? No. I would have thought that they already had that in one of these NVIDIA toolkits, especially the NV diffrast. Okay, maybe we can just load this at runtime here. First time running will take some time to compile the CUDA extensions. All right, so maybe let's just try to do that. Bash scripts install ext.sh. Torch 1.12. So okay, so this is failing from that same error. So yeah, this is, we have Torch 1.12.1 plus CUDA 10.2. That's not what we want. Let's pip uninstall Torch. Let's move this up here so you guys can see. Pip uninstall Torch. Yep, we want to uninstall it. And then we want to pip install Torch CUDA 116. Yeah, because we want Torch 1.12 and CUDA 11.6. Downloading, downloading. All right. Let's go back and look at this paper a little bit while that loads. Comparison of 2D sampling methods from text-to-image diffusion model with a text, a photo of a tree frog wearing a sweater. For score distillation sampling, as an example, we use an image generator that restricts images to be... Okay, that's kind of cool. Huh. I was going to say, do they use that symmetry constraint in these? Because it doesn't seem like it, right? This image is not symmetric. This image here is not symmetric. This image is symmetric. Interesting. Okay, I wonder if that's kind of a little trick that they use here. Okay. This figure looks like it gives us the right idea here. DreamFusion generates 3D objects from a natural language caption, such as a DSLR photo of a peacock on a surfboard, which is what they have here. Pip's dependency does not take into account error. Okay, I think we might have fucked up here too. Python import torch version. Okay, we do have a Torch version that works, but it's a little too new. Let's uninstall Torch again. Let's see if we can actually salt Torch. Can we just make up the version here? 1.12.1 plus Q 116. Pip Torch release history. 1.12. But I want specific CUDA versions. PyTorch install with pip specific CUDA. previous PyTorch versions. Linux and Windows, CUDA 11.6. All right, here, boom, this is what we want. Okay. So damn, 1.9 gigabytes. That is huge. Okay, but this is the version that we actually want, so we'll leave it there. I kind of want to read this article here. I'm curious. Maybe we'll leave that for another day. Maybe tomorrow. Maybe tomorrow we look at this. This is a real deep dive of assigned distance functions. Okay, let's go back to this graph in the paper here, or this figure in the paper that we were looking at. Okay, so it installed Torch 0.12. Let's see if these installation scripts work now. Hopefully they don't error out because we have the wrong PyTorch version. All right, well, that's going ahead. The scene represented by a neural radiance field. It's randomly initialized. Okay, randomly initialized and trained from scratch for each caption. Interesting. Our nerf parameterizes volumetric density and albedo color with an MLP. Yeah, so if you guys remember from one of the previous papers that we had, or that we were looking at, I don't know why this is grayed out. Okay, here we go. Go back to our library. Real image editing with diffusion models. I think it was this one. Yeah. Or no, it was not this. It was General Nerf. Yeah. This paper. So when we were looking at this paper, right, no, might not have even been this paper. All right. I don't know what the hell I'm talking about, but basically the nerf not only outputs the color at each individual point along a ray that is casted out from the camera, it also calculates something. You can also calculate arbitrary things. And what people choose to render in addition to color are a bunch of 3D modeling things such as albedo and density. So here you see the color, the albedo, the density. I suppose from these you can get the normals, get the shading. We render the nerf from a random camera using normals computed from the gradients of the density to shade the scene with a random lighting direction. Okay, so that's interesting. Shading reveals geometric details that are ambiguous from a single viewpoint. To compute parameter updates, DreamFusion diffuses the rendering and reconstructs it with a frozen conditional image gen model. Okay, so they're not fine-tuning the image gen model to predict the injected noise. yeah, so this is where they use the image gen model. They take the rendered image that comes out of this whole NERF pipeline that they created, they combine it right with noise that they sample from a normal distribution. Now you have the combined rendered image and the noise. Image gen will take the text embedding, right? And from that, try to pick apart the noise and then try to unapply the noise, right? Or otherwise predicting the injected noise. Low variance update direction that is back propagated through the rendering process to upgrade the NERF MLP parameters. Okay, so somehow they're taking the gradients from this and back propagating it to train the NERF. I think we're going to have to read this paper. This is, we do not need to back propagate through the diffusion model. Yeah, so they're not back propagating through here. They're back propagating through the NERF, which is kind of weird. I don't know how you can get the gradients to go all the way back to that. That seems like a long way to go. All right, luckily it looks like all this stuff worked, so it's good to see. Let's go back and see if we can actually run something while we take a little break here. Train with a text prompt. All right, copy paste that as we are to do. Okay, it's loading Stable Diffusion. It's downloading the Stable Diffusion model, right, which is going to replace our ImageGen diffusion model. While this loads, I will be back. I'm going to go to the bathroom. All right, this is kind of unfortunately what I thought was going to happen. That going to run out of CUDA memory. So this computer has a small GPU, and this happened when I was looking at Stable Diffusion on this computer, that it's just too, the GPU is just too crappy for the these models. It just doesn't have enough memory. That's unfortunate. I don't think we're going to be able to do anything interesting here with this. Let's see if maybe we can try some of these other things here. How to get past PyTorch. Oh. Oh, we have a little GUI. All right. Maybe if we just go depth, right? That's only one channel. It's going to be less. Debug. Camera pose. Let's hit start. No, out of memory again. Some just like slightly above 8 gigs. How to use CUDA out of memory workaround. Yeah, these people are just saying kill things, empty the cache, lower the batch size. This might be what we actually can do. I think maybe if we have multiple, if we put another GPU in this computer, even though it's another shitty GPU, max split size. If reserved memory is greater than the allocated memory, so reserved is 5.54, 5.38 is allocated. Okay. Try setting max split size to avoid fragmentation. Let's try that. Let's try to run this exact same command, except we'll set this CUDA alloc conf environment variable here. Let's see if that works. All right, so we got our little GUI. Where did it pop up? Here we go. Let's again try just depth mode for the single channel. FOV vertical, DT gamma, max steps. All right, start. Out of memory. So let's see if maybe we can reduce the batch size or something here. Pred image 512 train step. So sd.py in train step. Maybe we can reduce the dimensionality of these things and we can get something here. So nerf sd.py. Guidance scale, interpolate to 512 by 512 to be fed into the VAE. Produce latent prompt to image. So why don't we control F this entire repo for 512. And let's do something absolutely insane here, and let's just replace 512 with 256, which is half. This might just completely break, or it might just give us a this isn't even the right size error. But we'll see. Maybe it being smaller helps us a little bit. It might also be just that Stable Diffusion itself is too... Oh, there we go! Alrighty. So we decrease the size of this, and it's now training. We can actually see the learning rate going down, or kind of changing here. This is interesting. There's some kind of learning rate scheduling. Looks like it's decreasing over time, right? So initially you're taking more and more steps, right? You're taking big steps, and then over time you take increasingly smaller steps. Again, and what is this training? It's not actually pushing any gradients to the diffusion model, which is Stable Diffusion here. What it's going to be pushing gradients into is the nerf model. This is using floating point 16. How many epochs are there here? Let's see if we can find... Control-Shift-F. Epoch. For epoch range in max epochs. Max epochs, epochs. Iters.steps. Sorry about that. Hopefully I didn't blow out your ears. All right. Let's look for this variable steps. Training options, max steps. Damn. Okay. So decrease this if CUDA is Okay, so maybe we could have just decreased that to begin with. Let's actually Control C out of this. Sudo pkill python star. It's our GPU has officially killed that. That's what the sudo pkill python star does. It'll kill any running Python process, which usually is PyTorch. Okay, so actually let's go here and undo this change that we did. Are replacing every instance of 512 with 256. I think we're just going to try to lower the render width here, which is what they suggest for the CUDA out of memory. Let's make this a little bit bigger. Okay, so I'll put that in the background here. Let's use the little GUI as well. So let's go ahead and we'll say W, and instead of 64, we'll do half of that, 32. And then instead of 64 for the height, we'll do again 32. Then only valid when using CUDA rays. CUDA rays. Use CUDA ray marching instead of PyTorch. Maybe we'll try that out next. Training itters. Okay, 110,000. So that seems really fucking high. Let's just do 100. In fact, let's just do 10. Let's crank up the learning rate too. Let's do 0.01. Make it a big learning rate. Backbone, grid. So the Nerf backbone you want to use, grid, TCNN, or just the vanilla. Adds jitter to the randomly sampled camera poses. And then maybe max step here. Okay, actually these are only valid when sampling with CUDA Ray, which we don't have. Okay. Let's try this version using the GUI. Go ahead and hit start. CUDA out of memory. Let's try to be even more aggressive here. We'll do 16 by 16. It's not like that mattered. Let's go ahead and redo our little hack here. Let's replace 512 by 256. And then get rid of this W and H. Let's do that. I think you guys also have a hard time seeing this terminal when it's all the way at the bottom there. So let me put it there so it's a little bit easier to see. Okay, let's hit the start button again here. What is going on here? How do we get this to work beforehand? That doesn't make any sense. Okay, loading latest checkpoint. So let's see, trial checkpoints. It's trial checkpoints. Yeah, so I think these checkpoints might be screwing things up here. Remove star, or remove trial checkpoints star. Alright, so now we no longer have any of these weird checkpoints that it's trying to use. It's going to do it from scratch. Let's see if that fixes these issues. Yep, there you go. No checkpoint found. Model randomly initialized. All right, we're hitting start here, and we got it. We got something. Ooh, you can see that this little GUI isn't rendered separately from the training, so moving things within the GUI takes a second. So we should only be doing 100 steps. Right, iters 10. In fact, it should just be 10 steps. I wish this could somehow tell you how many steps there are. We can look here at the GPU utilization. We're kind of hovering around the cap here, right? Really utilizing the shit out of our little 1080, 73% GPU fan, 100% GPU utilization, so we're doing work. I don't know how long this is going to take, so we're just going to kind of leave that in the background, and then we're going to look at this paper a little bit more. Okay. Now that we have demonstrated how a diffusion model can be used as a loss within a generic continuous optimization to generate samples, we will construct our specific algorithm that allows us to generate 3D assets from text. Okay. We only use the 64 by 64 base model. Okay, no super resolution cascade. So, yeah, this is what we saw yesterday in the, maybe it wasn't yesterday, but in another Google paper where they used text to edit images, right, we found out that all the actual generative part of the problem was being done at a very low resolution, 64 by 64, and then they had two separate super resolution models that would then increase the resolution until you get an image that actually looks like something and it's not just some little tiny CFAR smear, right? So here they're only using the 64 by 64 model. They're not using the super resolution models. Use the pre-trained model as is with no modifications. That seems like an opportunity for improvement there. Score distillation loss function. Repeatedly render views of that nerf from random camera angles. My computer's dying here. What's going on? Random camera positions and angles, and using these renderings as the input to our score distillation loss function that wraps around image gen. So SDS loss. I think that's what this is. LSDS, the loss SDS. It's a nice description of how nerf rendering works. Yep, the opaqueness, here they're calling it volumetric density, RGB color. Okay, let's figure out more what this LSDS is. I think this is kind of the meat. How can we sample in parameter space, not pixel space? Okay, so they say diffusion models trained on pixels have traditionally been used to sample only pixels. Such models can be specified as a differentiable image parameterization. Okay, DIP from some earlier paper here, where a differentiable generator G transforms parameters phi or theta to create an image. All right, so you have some neural network that parameterized by theta and takes X, or not parameterized by theta, but it actually takes some parameters theta, so the input is theta. For 3D, we let theta be parameters of a 3D volume and G a volumetric renderer. Yeah, to learn these parameters, we require a loss function that can be applied to diffusion models. To enable tractable sampling via optimization, a loss function that, when minimized, yields a sample. We optimize over parameters theta such that looks like a sample from the frozen. Oh, CUDA out of memory. Okay, so it seemed like it was training there, so something happened. What happened? So likely what happened is that we were only doing kind of an initial part of the training, and then to do kind of a second part of the training, a new model was loaded onto the graphics card, or perhaps a new batch of slightly different data. Maybe the images that come out of this were loaded onto the graphics card, and there wasn't any more memory to load that new stuff. So that, or there's a memory leak where kind of the way the training loop was implemented, some stuff never gets recycled or garbage collected, and then over the course of the training you start using more and more of your GPU memory. But that stuff usually would have been found when the authors made this paper, or this isn't the official implementation. So whenever this guy created this repo, he would have found that pretty quick, especially if he was training this for a very long time. Although the V100, especially if he has one that has 32 gigs, maybe he just didn't realize that there was a little leak, a memory leak that was slowly accumulating over the course of the training. But I suspect that it's just what happened is we got to a secondary part of the training, right? So maybe the first part that we were doing here is we just loaded the image gen model, and then we were feeding these images to get these, and then now that we have all of these, now we're trying to backpropagate, so then it loads the nerf model, and then by trying to load the nerf model, it runs out of memory. Okay, so train step. And then within the nerf, it's trying to load the UNet, right? This UNet right here. And forward call. Yeah, so, all right, so it seems like we were actually just doing this part here. And then when it tries to perform inference, right, a forward step through this UNet, it probably tried to load the UNet, and then there wasn't enough memory in the graphics card. Yeah, so back to the paper here. It's interesting that they train this nerf MLP from random initialization, and they train it for every single image, right? I feel like there's probably so much to be gained by making that nerf MLP significantly larger, perhaps even a transformer, and then pre-training it on millions of objects, right? Just think about how much more powerful it would be if you did that. Of course, we're kind of years away from that. We need more powerful GPUs. We need more, perhaps improvements in the nerf algorithm itself. But damn, it just seems like there's so much more room to grow in this nerf rendering. Emit radiance. Okay, this is interesting. So normally nerfs, right? Like one of the things that is expensive to calculate in kind of the traditional rendering pipeline, where you have a mesh with triangles and then you have external lighting, is that the lighting is calculated, right? Like the light bounces off triangle meshes, right? And given the normal angle of the mesh and then a property of that mesh, for example, the specularity, the metallicness, how much that surface reflects light, allows you to calculate how much light you would be seeing at the camera, right? So from the camera viewpoint, how much of the light, given the light's position and the position of the mesh and the normal angle, and the normal of that mesh, how much do you see? And nerfs don't want to have to calculate all that, so they basically, one of the things they do is they basically predict how much light would be coming out just directly. But it seems like what they're doing here is that they don't care about that, right? And they actually directly parameterize the color of the surface, and then they use a separate shading process to determine how that mesh is going to interact with a light that is another object in this scene. Yeah, so this is kind of what I'm saying here. Requires a normal vector indicating the orientation of the object's directory, right? You need to know, is this surface, like, how is it angled relative to the camera, such that you have different, even just here with my hand, right? You can see that as I angle it differently, the light, which is over here, right, is going to angle or is going to interact differently with that surface. Huh. We find it beneficial to randomly replace the albedo color P with white to produce a textureless shaded output. This prevents the model from producing a degenerate solution in which the scene content is drawn onto flat geometry to satisfy the text conditioning. So actually that's quite interesting, because isn't that kind of what this looks like? Right? It looks like it's trying to render flat 2D images at just different angles. So let's actually Control F the code and see if we can find that random replacement of the albedo. 1, 1, 1. 1, 1, 1. Albedo. Shading equals albedo. Sigmoid. Okay, so they're taking, this is the forward step of the, what is this? The nerf renderer. So the nerf model, this is the forward step, and in the forward step you have the n by 3. I think this is the, so D is the view direction, this is the position, and this is the plane light direction. No shading, 0, only shading. Textureless, albedo only. There's a couple different types of shading here. Let's go to common forward. So it doesn't actually look like they do anything. Actually, I feel like here is where we would randomly change albedo to 1. Okay. GitHub Copilot trying to guess what we're trying to do here. Randomly replace the albedo color with white to produce a textureless shaded output. Ah, okay, wait, so that's probably what textureless means. Only shading, textureless. Okay. Man, these results are just super awesome. I don't want to, like, is this guy publishing more research? Pinned. Retweeted a 2-minute papers summary of this. More retweeting other work. Stable diffusion plus jacks. Interesting. What's this? Diffuser 0.5 now supports jacks. What does that mean? Is this even free? No, I don't think we can have access to free TPUs. I don't know what this guy's talking about. Cost of TPU in Colab. TPU v4, about $1 an hour. I mean, that's pretty cheap, but it's not free, you know. The difference between $1 an hour and free is huge. Okay, I don't know. We're kind of getting to the end here. Unfortunately, we weren't able to get to a point where we generated something cool here. I really need to upgrade the GPU on this machine. I do have much bigger GPUs, just I don't have my streaming set up on the machine with the bigger GPU, so I'm gonna have to go ahead and swap that from the other computer. Maybe I'll try to put 2 GPUs in this computer, see what happens. I don't know if that might just make it worse, right? Multi-GPU setups are not the same as single GPU setups, and like partitioning across those devices is not necessarily automatic, right? Sometimes you have to be explicit, you have to start changing the code in order to do that, and it just makes it more annoying. It's easier to just have one GPU that has way more memory. But I'll go ahead and do that. I think this is an interesting, really, really interesting kind of thread of research. I think 3D diffusion models are going to be just absolutely massive. Like, this is our future. This is what the metaverse leads to, is basically you talk to your VR headset and it generates exactly what you want. Cool. Thanks for talking. Thanks for listening. And